Today is March 30th. It's our official start of quarter 4. We're going to be talking about the vocabulary of acids and bases. So the essential questions we're going to try and answer are: what are 9 properties of acids and 9 properties of bases? What are the different definitions of acid and bases? And what makes them strong or weak? What is the pH scale and how are pH and pOH calculated? Our student performance expectations: students should be able to compare the products of acidic, basic, and neutral solutions, distinguish between Arrhenius and Bronsted-Lowry models of acids and bases. And for homework, down here in the blue, we're asking that you use your home textbook to look through pages 637 to 646 and complete essential questions 1 through 3, 7 and 8, and then practice problems 1 and 2. That's all in the study guide. If you didn't get a study guide before we left for break, it's in the library tab on Edsby. The last thing, this is what you're going to actually turn into us before tomorrow morning, so by 11:30 tonight, is these 2 learn activities on Quizlet. So acid-base vocab day 1 and acid-base vocab day 2. A lot of you have already done this over last week, so don't worry about it. But if you did not get credit for doing this last week, then you need to complete this tonight. So acids and bases, unit 14. An operational definition defines the term by its properties. Acid properties have a sour taste. Vinegar is a solution of acetic acid. Citrus fruits contain citric acid. Acids react with certain metals to produce hydrogen gas. Acids react with carbonates and bicarbonates to produce carbon dioxide gas. Base properties: they have a bitter taste, they feel slippery, and many soaps contain bases. As we go through the PowerPoint slide, you might see this hand up here in the corner or somewhere on the slide. Whenever you see this hand, that means that you need to copy this down into your notes. So it means this slide is important and all the information on here needs to go into your notes. So these are your properties of acids and bases. Our 9 properties are: they taste sour, corrode metal producing hydrogen gas, reacts with carbonates and bicarbonates to produce carbon dioxide gas, increase the hydrogen ion concentration as hydronium ions in water. The hydronium ion and the hydrogen ion is a hydrogen ion attached to a water molecule. So water we know is H2O. If I add an extra hydrogen, that's how we get our hydronium, H3O. Acids also react with bases to form a salt and water. This is called a neutralization reaction. We'll talk about this more later. pH is less than 7. Turns blue litmus paper to red, blue to red, acid. Is colorless with phenolphthalein. That's an indicator, just like litmus paper. We'll talk more about indicators a little later in the week. And it is an electrolyte. It dissolves in water and conducts electricity. Hydrogen ions are going to come off in water, so all acids are going to have a hydrogen ion come off. And in this picture here, we've got a drawing of our citric acid. So this hydrogen here and this hydrogen here and this hydrogen here can all come off pretty easily. So usually all three of them won't, just one. The first one will come off a little easier, the second one a little harder. We'll talk more about that later. And it says the tartness of lemons and oranges comes from the weak acid, citric acid. The acid is found widely in nature and in many consumer products. The sting of ants is also due to a weak acid, formic acid, and so this hydrogen in formic acid is going to be the one that comes off easily. So you might notice the hydrogens, the structural, I'm choosing a hydrogen attached to an oxygen that's attached to a carbon that's also double bonded to an oxygen. So we have that same group so I'm looking for this COOH. There's one there, there's one there, and here's one here. Let's get our properties of bases. Our 9 properties are: they taste bitter, chalky, they feel soapy or slippery, they produce hydroxyl or hydroxide ions in water, our hydrogen ion concentration is less than 0.0000001 molarity. They react with acids to form salts and water. Their pH is greater than 7. They turn red litmus paper to blue, so we say basic blue. Some bases are colorless and some bases are hot pink in phenolphthalein, and they're electrolytes. And for our picture, we've got a caffeine molecule. So caffeine is a well-known stimulant and a weak base. Our next definition, so we got our operational definition of an acid. Now we're going to get the Arrhenius definition of an acid. Arrhenius definition of an acid is that it gives off a hydrogen ion and forms hydronium ions and increases the hydronium ion concentration when dissolved in water. So hydronium ion concentration increases while the hydroxide ion concentration decreases. Acids cause the hydronium ion concentration to increase while the hydroxide ion concentration decreases. And we put a little teeter-totter here to show that our hydronium concentration is higher, and so the hydroxide must be lower. Let's get our Bronsted-Lowry acid and Lewis acid definitions as well. So the hydrochloric acid is a strong acid. We have the equation here, hydrochloric acid plus water, and then the hydrochloric acid breaks apart. But then we're showing it one step further. So this shows the hydrochloric acid breaking apart. But this hydrogen here doesn't really float around by itself. It actually is going to attach to the water. So really what you end up getting is this hydronium and then the chlorine by itself. So our hydrogen ion is accepted by the water to form a hydronium ion. hydrogen ion is just a hydrogen ion, which is just a proton. Remember, hydrogen only has one proton. Since it has a positive charge, that means it lost one electron. But if it lost one electron, then it has no electrons, so it's literally just a proton. If you're more of a visual person, this picture here might help. It shows the hydrogen here, and then on the other side it shows that it's attached to the water. Our Bronsted-Lowry definition of an acid is a compound that donates hydrogen ions or loses a hydrogen ion, which is also a proton donor, since our hydrogen ions are just protons. So our Bronsted-Lowry definition is a proton donor. Our Lewis definition of an acid is an electron cloud finder or electron pair acceptor. All right, let's get our Arrhenius base. Arrhenius definition of a base: they give off hydroxide when dissolved in water. Hydroxide ion concentration will therefore be higher up on our teeter-totter, and the hydronium ion will be lower. An Arrhenius base causes the hydroxide ion concentration to increase, while there's a decrease in the hydronium ion concentration. So Arrhenius definition of a base in water, we said increases the hydroxide ion concentration. So here's some examples. I have sodium hydroxide, and that'll break apart into sodium and hydroxide. So now we have more hydroxide. Calcium hydroxide, since calcium has a +2 charge, it has 2 of these hydroxides attached to it. So when it breaks apart, you'll get 1 calcium and 2 hydroxides. Bronsted-Lowry definition of a base is a proton acceptor. So remember, our acid was a proton donor. Our Bronsted-Lowry definition is going to be a proton acceptor. So our example we have here is ammonia. So NH3 is ammonia. Well, because this nitrogen has a lone pair on it, it's going to go and attack this positive hydrogen ion. And then we end up with ammonium on the other side. Our Lewis definition of a base is an electron cloud provider or electron pair acceptor. So again, our ammonia here, NH3, had that electron cloud, and it provided that to attach to the hydrogen ions. What makes an acid strong? Our definition of a strong acid: our strong acids dissociate or fall apart or ionize completely in water. The anion, which is the negative ion, is too weak to hold on to hydrogen's proton. What makes an acid weak is weak acids only partially dissociate, fall apart, or ionize in water. The anion is strong enough to hold on to some of the hydrogens. So remember, if our definition of an acid is that it produces hydrogens, if are anions strong enough to hold on to those hydrogen ions, then they won't go into the water. So strong acids break apart completely, weak acids only partially. Go ahead and get these examples of acids down. So our 6 strong acids, we have hydrochloric acid, chloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and the first hydrogen from sulfuric acid. And we'll talk a little bit more about this. You can see that there are 2 hydrogens. So the first one that comes off completely. So the first hydrogen is strong. The second one, only some of it comes off. So that second one is weak. Our weak acids, we have hydrofluoric acid, hydrocyanic acid, carbonic acid, phosphoric acid, acetic acid, nitrous acid, and sulfurous acid. And then organic compounds. So our organic compounds have this COOH on them. So remember I circled these before, these COOHs. This hydrogen here is going to fall off easier. And we can see in our acetic acid, which is one of the polyatomic ions you guys memorized, it has this COOH group on it. So you might remember seeing it written as C2O2H4. So a lot of times it will be written more simply like this, CH3 with COOH, so that you can clearly see, oh, it has that COOH group and therefore is an acid. R, so when we're looking at our organic acids, so it says R here, R can be literally anything. So it can be as simple, if we're looking at our ant up here, it's as simple as a hydrogen. We have COOH attached to a hydrogen. Or if I'm looking at this COOH group, it would literally be all the rest of this. So R is just anything attached to that. And then up top, to help us differentiate between our strong and our weak, it says if I have 10,000 hydrobromic acid molecules, all 10,000 will dissociate. Because it's a strong acid, all of them break apart. If you have 10,000 chloric acids molecules, all 10,000 will dissociate. Again, that's a strong acid. All of them are going to break apart. You would have no chloric acid molecules, and you would have 10,000 hydrogen ions and 10,000 chlorate ions. On the bottom, now we have our weak acids. So if you have 10,000 hydrofluoric acid molecules, only 266 will be dissociated. So only 266 will break apart into their hydrogen and their fluorine molecules. If I have 10,000 acetic acid molecules, only 42 will be dissociated at any given time. All right, now let's look at bases. What makes a base strong? Just like acids, strong bases are going to dissociate or fall apart or ionize completely in water. The anion, usually the hydroxide ion, is too weak to hold on to the cation. And what makes a base weak? Well, just like with an acid, weak bases only partially dissociate. So the anion is strong and it holds on to that cation compared to water's attraction to the cation. For our strong bases, we want you to get 10 of them. So we've listed 5: sodium hydroxide, lithium hydroxide, potassium hydroxide. Those are all from group 1. In group 2 on our periodic table, we have magnesium hydroxide. Because it's in group 2, it has a +2 charge, which means it's going to need 2 of these OH minuses to cancel it out. Same with calcium. Group 2, it has a +2 charge. We need 2 of those -1 hydroxide ions to cancel it out. And then it says to add 5 more. So group 1, like sodium, lithium, and potassium, and group 2, like magnesium and calcium. So those metals with a hydroxide, that OH, are strong bases. So write down 5 more bases from group 1 and group 2. For weak bases, we've got ammonia, which is NH3, amines, which are very similar to NH3, except now that nitrogen's attached to something else, and so we just have NH2, and then that line on the left is showing it's attached to something else. Amides, so now our nitrogen is attached to 2 other things, which we can see in our caffeine. So on our caffeine molecule, we have these nitrogens attached to other things. And alcohols, so chemicals that have COH. So remember our acid, we had that COOH. This is just COH, and it acts like a very weak base. All right, conjugate pairs. So Bronsted-Lowry has conjugate pairs, and they have the same anion, so the same negative anion, but a different number of hydrogens. So we've highlighted for you this conjugate pair. So this anion and this anion are the same. The only difference is the one on the left has an extra hydrogen, so it gets to be the acid of the pair. When we look at the pairs, the one with the more hydrogens is the acid. If you're more of a visual person, you can look down here. There's our carbonate ion, carbon with 3 oxygens. And over here, we have that same carbonate ion, but now there's a hydrogen attached. Our next conjugate pair, we have water on the left, and on the right, it has an extra hydrogen. So the one on the right gets to be the acid. We can also see that up here. H2O, now we have H3O, it has an extra hydrogen. And between the pair, whichever one of the pair has the extra hydrogen, that one gets to be the acid. So it says within a pair, the chemical with more hydrogens is the acid, and the chemical with few hydrogens is the base. within a conjugate pair, the chemical before the arrow is either the acid or the base, and the chemical after the arrow is either the conjugate acid or conjugate base. So if we look up here, it just says acid and base on the right, so let's go ahead and fix that. So to the right of our arrow, so we have our arrows here in our chemical equation, the right side, our products, will be called conjugate acid and conjugate base. All right, let's look at some other pairs. So our first equation, we have HCl, hydrochloric acid, and KOH, potassium hydroxide. And then we get HOH and KCl. So first it wants us to connect the conjugates. So we're going to look at the ones that look the same except there's an extra hydrogen. So this first one, I see the chlorine, so I'm going to go find the other chlorine anion, and it's right there. Here we have our hydroxides, so we can connect those. So we distinguish that KOH is our base. You would have known that just from memorization, but the HOH, which is just water, has an extra hydrogen. So this hydrogen here, on the left we just have OH, on the right we have HOH. There's that extra hydrogen. Alright, if we look at our next pair, the acid is the one on the left, because on the right we have potassium chlorate, on the left there's hydrogen, so the hydrogen, there's an extra hydrogen on the left. Alright, here is our next equation. So we have sodium carbonate. So let's attach it. Where is there another carbonate, and the only difference is the number of hydrogens? So there's the other carbonate ion. Remember, we're looking for the anion, which is the negative ion, which will always be listed second. Now, the one with the most hydrogens gets to be the acid. There's more hydrogens on which side? The one on the right. And because it's to the right of the arrow, it's not the acid, but a conjugate acid, meaning the one on the left is our base. Alright, let's line up. We have the chlorine anion, and here's the chlorine anion. The one with the most hydrogens gets to be the acid, so that's the one on the left, which means the one on the right will be the base, but remember it's to the right, so we call it a conjugate base. Alright, let's look at our anions again. Do we see matching anions on both sides? So this H2O, which one looks similar to H2O on the other side? So H3O looks just like H2O, but it's got an extra hydrogen. So that one gets to be the acid, and the water on the left will be our base. And remember, because the hydronium ion is on the right, we're going to call it the conjugate acid. And since we had conjugate acid, the other one has to be a conjugate base. And since we have the base on the left, the other one's going to have to be our acid. And in fact, we learned that H2SO4 was a strong acid. They would have also paired up because they both have this sulfate ion. Conjugate acid-base pairs, this one you are going to do. I'm also going to ask that you throw in one additional thing. So strong acids have weak conjugate bases. Weak acids have strong conjugate bases. Strong bases will have weak conjugate acids, and weak bases have strong conjugate acids. So you'll need to look back at the acids and bases that we wrote down as being strong. And when you pair them up, acids become bases, strong becomes weak. Bases become acids, and weak becomes strong. So they're going to be opposites. So once you've found the pair, they'll be opposites. Determine the acid, the other one in the pair is the base. If one of them you know is strong because we've memorized it as strong, the other one will be weak. All right. Again, we have this hand here, which means you are going to write this down. So write these down, match up your conjugate pairs. Whichever one has the most hydrogens gets to be the acid between the pair, and the other one gets to be the base. If you see one that you've memorized as strong, the other one in the pair will be weak. All right, our pH scale. pH is a measure of how acidic or basic a solution is. The pH scale ranges from 0 to 14. Acidic solutions have pH values below 7. A solution with a pH of 0 is very acidic. A solution with a pH of 7 is neutral. Pure water has a pH of 7. Basic solutions have pH values above 7. And a solution with a pH of 13 to 14 is very basic. So this pH scale on the left, it's showing our most acidic, our acids, are at the very top. So a pH of 0, so we've got hydrochloric acid. Right around 2, we've got lemon juice. Then we've got our vinegar, apples, tomatoes, bananas, milk, and then water. So the things we eat, most of the stuff we eat, is in this range. Then we get to our blood, which is slightly above 7. So remember, water is neutral. Pure water is neutral. Our blood is slightly above that, so it's slightly basic or alkaline. Then we have our cleaning products, baking soda, soap, ammonia, drain cleaner. All of those are basic. The pH scale is a way of expressing the strength of acids and bases. pH can be viewed as an abbreviation for the power of hydrogen, or more completely, the power of the concentration of hydrogen ions. 0 to 7 will be an acid, 7 is neutral, and 7 to 14 is a base. Go ahead and copy this slide down and press play when you're ready to move on. Our pH equation is equal to the negative log of our hydrogen ion concentration. So pH is the opposite of the power of 10 of the hydrogen ion concentration. So our log undoes that power of 10. So let's see what I'm talking about. If we have this first concentration, we can rewrite that into scientific notation. So I'm going to make a number between 1 and 10 by moving my decimal. So I need to move it 1, 2, 3, 4, 5 spots to the right, and that will get me 1. So 5 spots to the right, since this number is smaller than 1, we're going to use a negative exponent. So you would write 10 to the negative 5 molarity. If you take the negative log of that, it undoes, it's the opposite of our power of 10. So the log gets rid of this power of 10, and then because it's a negative log, that gets rid of the negative, leaving us with a pH of 5. All right, let's look at the next one. I have my concentration here. Let's get it to a number between 1 and 10. So move my decimal 1, 2, 3, 4, 5, 6, 7, 8 spots, which gives me 10 to the negative 8 molarity. When you take the log of that, it gets rid of the 10. And then the negative in front gets rid of the negative here, because a negative of a negative is a positive. So we get a pH of 8 when we take the negative log of 10 to the negative 8. All right, then it says a change of 1 pH unit represents a 10-fold change in the acidity of the solution. The two solutions change by 3 pH units, then that would be for every 1, since it's a change of 10. If I'm changing by 3, it would be 10 times 10 times 10 change in acidity. So 10 times 10 is 100, times 10 again is 1,000. So a pH change of 3 would be a change of 1,000. So if we are looking at, we had a pH of 5 on our first one and a pH of 8 for the second one. The difference between 8 and 5 is 3. But remember, when we did our pH, they came from our concentrations that were both powers of 10. So our pH change of 3 is really a change of 10 to the third, which is 1,000 times greater. So our first solution with our lower pH of 5 is 1,000 times more acidic than the second. A change of 1 pH unit represents a 10-fold change in the acidity of the solution. So let's compare gastric contents, so this is what's in your stomach, which has a pH of about 2, and the egg whites that someone might eat for breakfast, which has a pH of about 8. Which is more acidic? And then how many times more acidic is it? So if I'm comparing my pHs, are the higher numbers or the lower numbers more acidic? The lowest pH is the most acidic. Stomach acid's pH of 2 is less than egg white's pH of 8. Therefore, gastric contents is more acidic. So that's how it actually breaks down the food that you eat so you can get the nutrients from it. Well, let's see how many times more acidic it is. So our difference in pH from 2 to 8, if I do 8 minus 2, That gives me a pH change of 6. But remember, the concentration was an exponent of 10. So that pH is really going to give us a 10 to the 6th concentration change. So we did our pHs. The difference in pH was 6, but for concentration it's 10 to the 6th. So if you do 10 times 10 times 10 times 10 times 10 times 10, you would get 1 million times greater. So the stomach acid is 1 million times greater concentration of hydrogen ions. So these little brackets that are put around our hydrogen ion, that just means that it's the concentration of the hydrogen ions. All right, let's see if you can do this on your own now. A change of 1 pH unit represents a 10-fold change in acidity of the solution. All right, let's see. As the pH of a solution is changed from 4 to 9, how does the concentration of hydronium ions change? And how many times less acidic is it? So hopefully you saw it changed from 4 to 9. So that is a pH increase of 5 units. 10 to the 5th would be 100,000-fold decrease in hydrogen ions. The basic solution with a pH of 9 is 100,000 times less acidic than the original solution with a pH of 4. All right, let's talk about neutralization reactions. It's a special kind of double replacement reaction. Our neutralization reactions are always going to be an acid reacting with a base, and it will always make salt and water. So a reaction between an acid and a base is called neutralization because when you mix the two solutions, the acid with a low pH, the base with a higher pH, the ending result is not as acidic or basic as the individual starting solutions, and the resulting pH will be closer to 7. So we have our base on our left, which would be blue with our indicator. We have our acid on the right, which is red with our indicator. So this one is going to be universal indicator, which still just like litmus paper, basic blue, and then acids, blue to red, acid. And so when we put them together, we get a pH of 8. We started with 12 and 2, and they balance out to 8, which is pretty close to neutral. So this particular equation, we have our acid as hydrochloric acid and our base as sodium hydroxide. So remember when we did double rainbows, so I need to make my double rainbow, so I do my outsides and my insides. There's my double rainbow. If it was listed first, it stays first. So sodium was listed first, chlorine was listed second. So we want sodium first. Our metals and our positive cations are always listed first. So sodium chloride. And then H from the acid, the OH from the base is HOH, which can be rewritten as H2O. So neutralization, when a strong acid and a strong base neutralize each other, the products are always water, and salt. How is pH calculated? So we did this a little bit already, and you wrote down that pH is equal to the negative log of our hydrogen ion concentration. We also already mentioned that pH is a way to compare the concentrations of hydrogen ions or hydronium ions, we can use those terms interchangeably, in a water solution. The concentration of our hydrogen ion molarity is shown as brackets around that hydrogen ion concentration. So when you see this, it's giving you a concentration in molarity. And then here is our equation again. pH is the negative log of our concentration of hydrogen ions. And really our pH is just the exponent. So if our hydrogen ion concentration is 10 to the negative 4th molarity, then pH, you can type this into your calculator, the negative log of 10 to the negative 4th. But really you didn't actually even need a calculator. The log gets rid of that power of 10. And then if I take a negative of negative 4, you get 4. If the hydrogen ion concentration is 10 to the negative 13 molarity, then pH is equal to the negative log of 10 to the negative 13. And again, we can just take that exponent and get 13. So these are working out nice and easily because we can just get the exponent from them. But if I had any number in front that wasn't 1, so if I had like 2.5 times 10 to the negative 13, then it's not going to work out to these exact exponent numbers. So it might be helpful to start now learning how to punch this into a calculator and making sure you're getting the right answer. So go ahead and try with this one. If our hydronium ion concentration is equal to 10 to the negative 7th molarity, to find the pH, you would type in the negative log of 10 to the negative 7th. Once you finish typing that in the calculator, let's check. It should be just 7 because that was our exponent. All right, let's talk about what pOH is. So just like we had done with pH, pOH is a way to measure the concentration of hydroxide ions, the OH minus. The solution for the hydroxide ion concentration is equal to, and again we use brackets, this OH minus in brackets is our concentration of our hydroxide ions. And we're going to use the same equation, except now we'll take the negative log of our hydroxide ions. So if our hydroxide ion concentration is 10 to the negative 2 molarity, then pOH is the negative log of 10 to the negative 2. Again, practice typing this in your calculator to make sure you know how to do it correctly. But you should just get the exponent, which is 2. Try this one. Pause it now. Hopefully when you typed in the negative log of 10 to the negative 10, or if you saw that you're taking the log of 10, so those cancel, and a negative of negative 10 is just 10. And the last one, if our hydroxide ion concentration is 10 to the negative 7, then POH would be the negative log of 10 to the negative 7. And hopefully you got 7. All right, that's the end of our official day 1, March 30th. Hopefully you were able to answer these essential questions on the left. You should be able to do those student performance expectations on the right. And then don't forget this homework tonight. So we went over a lot of acid-base vocabulary. So in Quizlet, do day 1 and day 2, the learn activity. If you already did this last week, then you should see that you have a grade for it, and I'll just slide that grade over. If you've not done this, get this done tonight.